Okay, everyone, let's get started. We have a lot to cover today. So we left off here. Last class, we went over the transformer architecture. We went over what are the computations that happen in each of these boxes. We talked about the difference between the encoder and the decoder. And at the end of last class, we looked at this diagram, which is taken from the reading that you had, the original transformer paper, Attention is All You Need. This is what we talked about last time, right? So the encoder in the machine translation setting is responsible for computing useful representations of the French sentence, right? And then the decoder is responsible for actually producing the words that are associated with the English translation of that sentence. And the way in which these two networks are connected to each other is through the cross-attention, which is happening in the decoder, where the keys and the values come from the encoder's final layer hidden representations, and the queries come from the decoder's current hidden states, right? So the cross-attention is where the queries come from a different set of representations than the keys and values do. So we got up to this point, and at this point you should be able to roughly understand this diagram and all the different components and why they're together. Also note that the encoder is trained using the signal. So here in the machine translation setting, all of the error signal is computed at the top layer of the decoder, right? So the decoder is predicting the next word at every position. We can compute our cross entropy loss here, and then we backprop that loss function down through this softmax, through this linear layer, through all of these stacks of layers. And note that at every transformer block in the decoder, some of the gradient gets transferred over to the encoder as well through the cross-attention connections. So you're going to have some of the gradient signal flow into the encoder at every layer and adjust all of the encoder's parameters. So, you should consider yourselves lucky that you don't have to manually derive any of the gradients for something like this, as it's extremely complicated. Okay, so at this point, I wanted to talk about some of the different pieces of the transformer at a higher level. We've seen a lot of this before in the last class on the notes, but just to highlight some of this stuff in the slides using this figure. So first, I wanted to go over a nice visualization of self-attention. So you can imagine that these are the computations that happen in the encoder network of a transformer. So remember, in the encoder, we are using completely unmasked self-attention. So maybe, I would hope that these slides make it more clear exactly what's going on. So these slides were made by Emma Strubel, who did her PhD here at UMass and is now a professor at CMU. So imagine that the input to the encoder, so the network on the left over here, is the sentence Nobel Committee, or this partial sentence, Nobel Committee awards Strickland who advanced optics. So we want to pass this through multiple different layers of unmasked self-attention, and then finally get our final layer hidden representations. So let's say we're at some layer, so we have the output of the previous layer. So what we do is we do our query key value projections, right? We went over this. Each of these is done by a feed forward, like a linear layer, followed by a nonlinearity. We have these three separate weight matrices that are unique for this layer, right? And they're accomplishing this projection step. Now, for every position, we take the query vector and we compute the dot product between this query vector and all of the key vectors, right? So at the end of the day, we end up with the score here. This is after applying the softmax, so we get a distribution over all of the words in the sequence, right? And similarly, we get one of these for every single position in the sequence. So this distribution is a result of taking the dot product between the query vector at this position, all the key vectors, then applying the softmax, and then you get this distribution, right? So now we're going to use this distribution to compute the weighted average of the value vectors, right? So we do something like this, right? Where we use these weights where this weight here might be the weight of Nobel, this weight up here might be the weight of optics. We compute this weighted average of the value vectors. And then we get these outputs, the weighted average of the value vectors. So then the other thing we discussed was the multi-headed self-attention, right? So this is the computation that happens at one head. So if we wanted to do multiple heads, we basically just have a lot of these different query key value projections, one for each head. We do the same thing, so you can see that here for Nobel, these distributions all look different, right? Because each head is learning to look for some different property of the input text. And eventually we have all of these different weighted averages of the value vectors that are output from our multi-head self-attention. So of course, we eventually want to get, as an output of this self-attention block, a sequence of vectors that are of the same dimensionality as the input to this particular layer. So once we have our multi-head representations, the next thing we do is concatenate them and pass them through a feed-forward layer, right? This is representing the concatenation. This is the feed-forward layer. This gets the dimensionality of the concatenated vector down to the original dimensionality of the input. And after this, we apply our residual connection. So we add the input to the output, right? We talked about this as a way to improve the gradient flow of this model. Then we just stack many different layers of what we just described on top of each other until eventually, we get a sequence of these final layer hidden representations, which we can use for whatever task we want, right? So in what we've seen so far, this output of layer J here could form the input to the cross attention. So it could be used as keys and values of a decoder that's doing some sort of generation. Maybe it's translating the sentence or summarizing it or something. Okay, so hopefully this was helpful. Are there any questions on the basics of this kind of unmasked, multi-headed self-attention? Okay, so let's get back to this figure with that hopefully out of the way. So I just wanted to cover all the little things here again, just to make sure that you'll understand them properly. So at the very initial part of this network, before we go through any of these transformer blocks, we apply this positional embedding to every single one of the input word embeddings. Remember that these are embeddings that are traditionally the same size as that of the word embeddings, and they are just added. So these position embeddings could be learned. They could be a fixed function, as we'll see a little bit later. And there are many different, more complex types of position embeddings that we'll go over later in this semester. Some have very interesting impacts for downstream NLP applications. Without these positional encodings, note that the transformer is completely unaware of the order of the words in the sequence. So we need the position embeddings to inject some notion of order. Okay. So we talked about the residual connections, right? Those are modeled with these arrows over here. Those help the gradient flow. We talked about the feed-forward layer that is on top of the weighted average of the value vectors. In fact, on top of the concatenation of all the head representations. This feed-forward layer at each block, if you count up all the parameters in the model, this feed-forward layer, these feed-forward layers tend to dominate the parameter count. So the transformer's parameters are largely the feed-forward layer that occurs right after the concatenation of the head vectors. So this is where you get some size into your model. Okay, and we stack these transformer blocks on top of each other. We will talk about these scaling laws of language models later on in the semester, because I think a number of you had questions about why would you want to make your model bigger. It is really an empirical question that people have researched for the last couple of years, and we will discuss some more interesting insights from that. But the takeaway is bigger models are generally always better than smaller models when they're given enough data. And for language modeling, we have virtually infinite data. So if we are able to scale up our models to bigger and bigger sizes, our language model, empirically, it's been shown that they learn more and more useful linguistic information that can be transferred to solve other tasks. Okay. So the decoder then, when we were looking at the decoder, we noted that the first embedding, the first input in the decoder is always the start of sequence token. And that's because you want, when you're actually trying to generate some text from the model, you want to put in the start of sequence token and condition the model's prediction on that token. So it knows that this is the beginning of the sequence. And this is also helpful when you're applying masked self-attention, right? Because when you're doing the masking, the first position of the decoder is allowed to attend to itself because it's the start of sequence token. So at the first time step, the model sees the start of sequence token and is asked to predict the first word of the first real word of the output sequence. So you don't necessarily need to have a start of sequence token in the encoder, right? Because you're really not generating anything in the encoder. You do need it in the decoder to help with the masking and make sure you're not cheating when you implement the mask. Okay, so remember our mask looks something like this. So at every position in the decoder, our attention is only allowed to attend to that position and everything that occurred previously. It cannot look at things that happen in the future because its objective function is to predict the next word. So if it did, it would be cheating. Okay, so in the decoder, the very first attention block we see is masked self-attention. So here, the model is only looking at the previous words in the decoder's input. It isn't looking at the encoder's input at all, right? Right, and I guess this question I've answered multiple times before, so I'll skip it. Once we do this masked attention, then we move on to the cross attention. So we take the outputs of the masked self-attention, and then we use them to get query vectors, which we then use to compute the attention scores over the output of the encoder's final layer hidden states. Then after we stack up these decoder blocks, how many ever times we can fit into our GPU, we eventually get to the softmax layer, which is predicting the next word for every position of the decoder. Okay, so any questions about that? Okay, so the positional encodings in the original transformer paper, they did not learn them. So in many models nowadays, it's common to just say, okay, the maximum sequence length that my model can handle is, say, 2048 tokens. So I'm going to learn 2048 different position embeddings, one for each position. And my model is just going to be, so those are going to be learned through backprop. And at test time, this model is not going to be able to handle any sequences that are longer than 2048 tokens. So this is like the simplest thing that you could do, but it also has limitations, right? It cannot extend, the sequence length can't really extend easily past the maximum sequence length that the model was trained on. So another thing you could imagine doing is just concatenating some fixed value or adding a fixed value that corresponds to the position to every vector, right? So I could just concatenate the number 1, the number 2, the number 3 to each of the word embeddings at position 1, 2, and 3. I probably would want to normalize these values somehow, but then I don't have to learn these embeddings, and the model has some notion of position. However, this has the same problem as the learned embeddings, right? Where if you do this, you're not going to be able to generalize to sequences that are longer than what you trained on. And empirically, it seems to work better if you actually learn a full vector embedding of the position rather than these fixed values. Probably because there's some nice properties of relative position that the model can learn if you give it a full embedding versus just a fixed number. Okay, so the transformer intuitively is using a fixed function that gives you a vector for every position, which is of the same size as the word embeddings, the C sub i's in our notation. Intuitively, what you want is for the dimensions of this vector to somehow correspond to relative position. So you want to know, for example, if two words are right next to each other, you can tell in this like binary code example that, for example, 0, 1, if you look at the rightmost digit here, it flips with every word. So you can tell, whether or not a word is the same by, a word is adjacent to another word by looking at this rightmost digit here and then doing some simple arithmetic with the rest of this. So you can see also that the second digit here changes every 2 words. The third digit changes every 4 words, and so on. So with this kind of encoding scheme, you might hope that the model can generalize to even longer sequences than it's trained on if the model is able to pick up on these simple patterns. And the transformer's positional encoding is basically like a soft version of this. Instead of using binary codes, it uses sines and cosines to represent this kind of pattern. So this is the actual equation that you probably saw in the paper and wondered how did they come up with this. It's pretty unclear, and research since then has shown that there are many other functions that you can use for these position embeddings that work just as well, if not better. So we won't get into the actual details here, but note that every even dimension in these position embeddings is computed using the sine function. Every odd one is computed using the cosine function. And the actual position embeddings here look something like this. So each row here is the position embedding of one of the positions that are marked on the y-axis. So the top row is the very first position's embedding. You can see kind of the same sort of flipping of the dimensions, which indicate that they're relatively close or how close they are to each other. And you can hope that even if your model is trained on sequences of up to 40, the model can learn kind of how to manipulate these position embeddings to get relative position, even for sequences that are longer than that. In general, though, regardless of what position embeddings you use, your model is likely not going to be able to generalize very well to sequences that are longer than what it's trained on. We'll have a whole lecture later on in the semester about long context language models, which try and extend the sequence length to tens of thousands of tokens with various different modifications. But yeah, don't worry about understanding all the ins and outs of this function. We'll talk more about better ways to do position embeddings later on in the semester. So like I was saying, despite the flaws of lack of generalization to longer sequences, most models these days use, well, I guess nowadays things might be changing a little, but they use learned positional embeddings Specifically nowadays, people are using relative position embeddings, so not absolute position embeddings like these. We will talk about those more later in the semester. Okay, so I wanted to finish before I switch to the iPad with some of the hacks that you need to implement to get transformers to actually train properly. So we've talked about a lot of the architectural components, right? And you might, be thinking that, okay, all of these things are absolutely critical to getting this thing to work. But actually, these little hacks with which are, you can't really explain why they work, but they're all extremely important. So sometimes even more so than several of the architectural choices that we've already discussed in the transformer. So the first thing, and one of the weirdest things, is the optimizer and learning rate schedule that you need to use when you train a transformer. So in this class, when we talked about gradient descent, we only covered the stochastic gradient descent update rule, right? So at every time I compute the gradient for a batch or for a single example or whatever, I take a step in the direction of the negative gradient using a fixed learning rate, that eta term, right? And we said, this is a hyperparameter that we set once at the beginning of training, and it's the same throughout. That doesn't work at all to train a transformer. It's much too simple. So there's many different optimizers that people have developed that are more advanced learning rules, essentially, than the simple gradient descent. So Adam is learning different kind of learning rates per parameter. So every single dimension of the theta vector, the parameter vector, will have a different learning rate, and so you'll take a direct step in the direction of the negative gradient, but it'll vary depending on which parameter you are. But there's also an initial learning rate for Adam. This kind of initial learning rate, the base learning rate, is very important for training the transformer. So if you just keep it fixed all throughout training to a single value, the model doesn't train. And that seems a little crazy, but it's true. Like one of my own PhD students, when he joined, the very first thing I asked him to do was re-implement the transformer from scratch. And so he did everything from scratch, and all of his architecture, everything was implemented properly. The only thing he was missing was he was just using vanilla Adam without modifying the learning rate in this manner, and the model wouldn't train at all. So this is like a super critical hack. But basically, you want to start with a very small learning rate and warm it up to a high value within the first couple thousand iterations. And then you gradually reduce the learning rate after this point to some smaller value. So your curves look like this. And this kind of triangular learning rate is extremely important to getting this model to train. Before you ask, I don't know why this is important, and no one really knows. And it's also unclear how they even found that this is, the thing that gets the model to train. But yeah, it's very important. So I guess as a takeaway of this, you should know that a lot of these models are very brittle, and they do achieve impressive performance, but they also need to kind of be coaxed into training using tricks that we have no theoretical explanation for why they actually help. Okay, so another trick that is, so if you remember, the original transformer paper was doing machine translation. And so another trick that is used in this paper is called label smoothing. And this is not transformer specific, but it is a trick that lets you increase your translation quality for any sort of machine translation architecture. And it's called label smoothing. So if you remember, if we have an example like this, I went to class and took blank, and in your training data, you see the word notes following this prefix. Your ground truth probability distribution, the one that you want your model to predict, will have 100% of the probability mass on notes and 0 on every single other word. And we talked about how this, this is the maximum likelihood estimate, but it may not make sense all the time, right? So here, I don't know, is there another word that makes sense in this context? And took drugs, right? That is a syntactically correct sentence, even if it's unlikely, right? But you wouldn't want to assign 0 probability to it because it's still a valid sentence. So if you train the model in this way, and especially if you have a relatively small data set, your model can become irrationally overconfident on the prediction of the next word. And so this is the distribution, the ground truth distribution that we've been using with 100% probability on notes. And this is what happens when you apply label smoothing. So basically you subtract some fixed probability mass from the ground truth word. Here we subtracted 10% probability, and then we evenly distribute that probability over all of the rest of the words in the vocabulary. So now, even though cats does not make sense in this context, it has a 0.025 probability of, like the model is trained to put some probability mass on cats. So why does this work? That's a little unclear. I mean, the intuition is that you're penalizing the model for being overconfident, and if you train the model with these distributions, the model tends to become overconfident. But this curve shows you the merits of label smoothing. So here, you can see that the target word confidence with label smoothing applied, you get the lowest loss when your confidence in the ground truth word is like 20%. And if you're putting more than that probability on the correct next word, your loss starts to increase gradually, which means the model is penalizing you for being too overconfident in a particular word. So this is a nice trick that you can apply to any sort of text generation problem to reduce the chance that your model is overconfident. That said, I'm not sure how important it is when you have a large enough training data set, but for like your final projects, for example, it might be a useful trick. Do you have a question?
So when we do label smoothing, is there a way to distribute the mass to, like, instead of doing it equally?
Yeah, so the question is, in label smoothing, the way it's described is you just evenly distribute this probability mass that you stole from notes across the rest of the data set, but there could be a more intelligent way of doing this, right? You could distribute the mass to synonyms of notes or words with the same part of speech or something like that. I'm not sure if anyone has tried this. I imagine it doesn't make that much difference because already like label smoothing improves your results slightly, but not by a huge amount. So I wonder if the main benefit of it is just it makes a model less confident in bad predictions, and it doesn't actually matter which words are getting the alternate probability, the additional probability. But I'm not sure. There might be some research on this if you look up label smoothing that you can find. Did you have a question?
Yeah, so if you go back to the graph where it looks like the loss is minimized at about 20% confidence, does that mean that they stole like 80% of?
Oh, I see. So what does this mean? So basically, this is like, I think, an aggregate confidence of all the model's predictions. So many of these predictions are wrong. Like the highest probable word is not actually the correct word. And in this case, you benefit a lot from not being as confident, right? Because your prediction is wrong in general. So yeah, the plot is not saying that we stole 80% of the probability mass. This is just with a fixed value like 10% or something, this is what the loss curve looks like. Okay, so another question is, the transformer has all of these different components like the value vectors, the key vectors, the feed forward layers, the multiple heads. How does the order of these components matter? Are some of them more important than others? How do they even settle on this one architecture? So the initial transformer, you know, they did do a lot, they checked a lot of configurations kind of manually, and they found the one that seemed to work best for their machine translation task. And then everyone just started using that because, like, you know, it worked well, so why not? That said, this is not the best architecture that you can create with all of these components. And there's a branch of machine learning called neural architecture search, which its goal is to automatically find good architectures to solve various tasks. And so there is a lot of work on this for transformer variants, like what if I reorder some of these components or add some new blocks into the self-attention, the transformer block? Can I get even better performance? And in this paper that was published late last year, they showed that if you, so the nonlinearity in the transformer model is the rectified linear unit, or ReLU. And the normal transformer just applies the ReLU and then does it applies a ReLU after doing the feed-forward linear transformation. But if you actually square the outputs of the ReLU, so you do this nonlinearity and then you just square all the results, so like each number in the resulting vector is squared, it seems to help quite a lot. And this is something that no one would really think about because it makes, like, I don't know why you would think that this would help at all, but it somehow helps significantly. Another thing that this neural architecture search found was that after doing these query key and value projections, if you apply a convolution on top of that before computing the attention scores, this helps quite a lot. So again, this doesn't really make any intuitive sense why you would want this particular block here. You could probably try and come up with some explanations, but again, no one thought to try any of these things before some machine came and tried them, and then it seemed to, you know, work pretty well. It's kind of sad, but every time you have a question like, why is this component in a particular place in the network? The answer is probably it seemed to work well in the experiments, but we don't know anything more than that. And if you give a computer enough time, it can probably find a much better configuration. So yeah, that's so if you're interested in this, you can check out this paper and see how they actually apply the neural architecture search. All right. Am I even on this YouTube chat? Sorry, I want to make sure I'm not skipping questions. Looks like I'm fine. Okay. So some of the most popular transformer language models that have been released are OpenAI's GPT. So that was in June 2018. It was pretty big for the time, but now it's considered super small. It's 117 million parameters, trained on about 13 gigabytes of data. So this is 1 billion tokens. You can approximate like a token is a word, so 1 billion words. GPT-2 came out less than a year later. It had 1.5 billion parameters and was trained on 40 gigabytes of data. And then over a year later, in 2020, GPT-3 came out, which you can see they scaled it to like multiple orders of magnitude, 175 billion parameters, 500 gigabytes of data. So this is 300 billion words. So 300 times the training data of GPT, which was released like 2 years earlier. Since this point, of course, you can imagine what has happened. There are many bigger models that have been trained. But somewhat satisfyingly, we're starting to see fewer and fewer like actual significant gains on NLP tasks from just brute force scaling up these language models in terms of size and data. So the last couple years have seen, increased research in just scaling up transformers without any real thinking about, what intelligent modifications can we make to this architecture or to the training objective, because it just worked, right? So GPT-3, way better than GPT-2, which is way better than GPT. The the capabilities of each successive model were shockingly better than the previous one. But now we seem to have saturated to some point, and hopefully we can start doing interesting research again. So for you all in your project, GPT-2 is probably a very reasonable model for you to use if you're thinking about a text generation problem. It is available in the Hugging Face repository, which we used in our demo on the first day of class. And you can fine-tune it on Google Colab, at least a small version of it, and see how it does. GPT-3 now, I believe, is publicly accessible, but you can't actually access the model's parameters. They have an API by which you could access the model, and you have to pay after some amount of free credits have been exhausted. So this business model is kind of like language model as a service. This is a new thing. We'll see, how long that can actually be a financially viable option, but this is one of the better language models still that you can use. And so since it's publicly available now, all of you could try it out for at least on some small amount of data and see how it goes. So question, are we going to talk about OpenAI embedding? So OpenAI recently released embedding models that are derived from GPT-3. It's unclear how well they actually work, and they charge a whole lot of money for access to this. We will talk about this when we talk about retrieval models later on in the semester. Those embeddings are primarily used for retrieval, but not in any detail as they're literally just using the embeddings from GPT-3, so not particularly interesting. Okay, so we have a lot of different variants of transformers and modifications to the data that we're going to talk about. So for the rest of this lecture, we will talk about transfer learning using transformer-like models. We'll then talk about the importance of tokenization. Actually, I'm not sure what order we're going to do this in, but at some point we will talk about tokenization, which is how you actually segment your input. So as of now, we've been talking about our inputs are always words and we have word embeddings, but that's not actually how any of these models work. Their inputs are usually subwords and sometimes nowadays we have character or byte level models which have different properties. So we'll talk about that. And then several other interesting modifications of transformers and applications of them. So we're not going to actually talk in any detail about any other non-transformer based models. The field of NLP is basically run by transformers nowadays. So all of the new stuff we'll see in the rest of the semester just builds on top of these basically self-attention based models. Okay, any questions? I'm going to switch to the iPad while you come up with your questions. All right. Okay, no questions. All right, so I wanted to do a couple of things on the iPad. One thing that I think a lot of students in the past semesters that I've taught this class have struggled with is the different common types of transformers that you'll see in research papers. It becomes very hard to read a research paper when you have your conception of what this model is, like this encoder and decoder, and the paper is using it in a slightly different fashion, and you can't really follow, what the relevant components are doing. So I wanted to start with this and then shift from this to transfer learning using things like ELMo and BERT. All right. Whoa. Okay. So first we'll talk about common types of transformers. So the very first one is the simplest, and these are transformer encoders. And one example of this that we'll see later on in this class and then all of next class is called BERT. So a transformer encoder is just the encoder part of the diagram that we saw from the paper earlier in the slide. So basically, if I have my word embeddings here, I'm going to put them all into unmasked self-attention. I'm going to stack n of these unmasked self-attention blocks. And then at the end of the day, I'm going to come up with these final layer hidden vectors. And note that because I used unmasked self-attention, I can't actually predict the next word from these tokens, right? They have full knowledge of all the other words in the sentence, but still, these vectors can be very useful to solve other tasks that don't involve text generation. So these kind of transformer encoders are useful if we're interested in using the final layer token representations. So those are marked as these green things in the diagram, to solve downstream NLP tasks. We'll talk about what a downstream task is, but it basically is any non-self-supervised task, so something like text classification or question answering or something like that. As long as these tasks don't require generating text, you can get a lot of mileage out of transformer encoders using them strictly to learn representations of text. And then you have some other thing that is actually learning to use those representations to solve a task. So not useful for generation. Although this is kind of arguable, there have been papers, especially recently, showing that you can get high quality text generations from encoder-only models, but we'll talk about that also later in the semester. But in general, these are not as useful for generation tasks as what we'll talk about next, which is transformer decoders. So this is just the decoder part of the transformer network, but here we don't have the notion of cross-attention because it's not connected to any encoder. So this is just a language model. You'll also hear this referred to as a transformer LM. And an example of this kind of model is something like GPT-2. Which we discussed on the slide as one of OpenAI's models. All of the GPT, GPT-2, GPT-3 are transformer decoders. So they're transformer decoders that are just trained to predict the next word. So how do these work? Well, we can still take our same example from before. Here we feed this into, unlike the encoder where we used unmasked self-attention, here we're going to use masked self-attention. We're going to stack as many of these blocks as we want. Then we get these final layer token level representations. But now each one of these representations has information only about the current word and all the previous words, which is not the case in the encoder, right? Whoops. Let me go like this. So here the goal is actually to use these representations to generate some sort of text. So here we could produce C2, C3, C4, and C5. And so these kinds of models form the backbone of most text generation models. So useful to generate text. And these are trained via the language modeling objective. So I have yet to describe how these encoders can be trained by themselves, because you can't use a language modeling objective when you have unmasked self-attention. So we'll talk about how to train an encoder model at the end of this class, hopefully. But the decoder, we already know how to train, right? We just train it with next word prediction using the cross entropy loss and so on. So every time you see in a paper, if you're reading and you see we used a transformer decoder or a transformer language model to generate text, this is what you're referring to. There is no encoder component of this model. Okay, so then there's two other configurations that I think are worth mentioning. So another one is the transformer encoder decoder model. So this is what we saw in the original transformer paper, right? So here there's, some, let me go a little down. There's some input in, say, some different language, or there's some context. And then there's, I guess I should use okay, whatever. Then you want to produce some text in a different language. So here, the encoder part you don't want to generate. So the French words you don't want to generate. So again, here we're going to use unmasked self-attention, xn. We're going to get these vectors as output. And then on the decoder side, we're going to use masked self-attention followed by cross-attention. Right, so the cross-attention takes these encoder states into account. Then we're going to, produce these final layer vectors. And in the decoder side, we're going to actually predict the next word, right? So we're going to predict E1, E2, E3, E4. And again, these form a block that we will stop. So this is what we saw and covered throughout this class and the previous class. So this is not just useful for machine translation. One example of this that we will talk about in a couple of weeks is called T5. And there's also variants of T5, like multilingual T5 and so on. These are encoder-decoder models that are trained with a self-supervised objective like language modeling. So we will talk more about these later on in the semester. But in general, these kinds of transformer sequence-to-sequence models or encoder-decoder models are useful for conditional text generation. So remember that we talk about machine translation as one instance of conditional text generation, where you have some input context, which the encoder handles, and then you have something you want to generate conditioned on that context, like a translation. That's what the decoder is responsible for. Okay, so that one should be pretty clear. The last configuration that I want to talk about, which is just a variant of this decoder only model, is sometimes referred to as a prefix LM, or like a transformer prefix LM. And it's common to use something like GPT-2 you can fine tune it as a prefix LM. But basically, if we had the same exact input sequence, F1, F2, F3, start of sequence, E1, E2, E3, we can, if we don't want to have a separate encoder and decoder, we can also just use a single decoder to handle this entire input sequence. So if we wanted to do that, we can, instead of using fully unmasked or fully masked self-attention, we can use partially masked self-attention. Partially masked or partially unmasked self-attention. So we'll describe what this means in a bit, but at the output of this, I'm going to get a vector for every single word in the input sequence, and my goal is to do the prediction of the next word only on the English tokens that I actually want to generate. So I'm going to ignore all of these French tokens and then just generate E1, E2, E3, E4, and E5. So what does partially masked mean in this context? It means that regardless of where I am in the English sequence, I'm always going to be looking at, whoops. So like these three French tokens here are always going to be unmasked in the attention, regardless of what token I'm at. So F1, F2, F3, this is the input to my model, right? So I'm going to always look at them, and I'm going to apply the masking, like that triangular mask, only on the decoder side. So my mask, instead of looking like, maybe I'll use a different color. So if this is my original mask, where the colored in part is what the model is allowed to look at, so original mask. In this modified approach, I always look at the French tokens, and then I have this kind of mask here. So does that make sense? This is the prefix LM mask. And this lets me, with a single model, solve a conditional text generation task. Because whatever input I have, I can stick into the language model and process it with unmasked self-attention. And then whatever I'm actually trying to generate, like the translation, I can use masked self-attention to actually produce those tokens. So this is useful for conditional text generation. It's an alternative to the encoder decoder approach with just one model instead of two. So this approach and the previous approach basically are doing the same thing. The difference is that in the encoder-decoder model, I have a separate set of parameters for the encoder part. In this prefix LM variant, I'm using the same parameters to process both the input and the output. So in practice, they work very similarly to each other. In the T5 paper, which we'll cover in a bit, they showed that having a separate encoder and decoder is slightly better than doing this, but you will see both variants in practice, so it's important to know about them. Do you have a question?
Shouldn't the prefix tokens only replace, like only attend to only themselves? Because if they attend to elements on the decoder side, then that would convert the token.
Yeah, so the question is, shouldn't the prefix tokens attend only to themselves? And in this prefix mask, that's how it works, right? So if you look at the first block here, these, whoops. So this transition point here, from where you go from fully unmasked attention to masked attention, this occurs at the boundary between the input sequence and the output sequence. So the prefix tokens, the input tokens are allowed to attend to each other, but they do not see anything of the output sequence to prevent that problem. Other questions? Yeah.
What is the difference between a prefix LM and the transformer decoder or transformer LM?
Yeah, so that's a good question. The question is, what is the difference between this prefix LM and the transformer decoder? So the transformer decoder is generally used as just a language model which you can generate from, and you can put as much context into this language model as you want and generate the next word. The only difference is that in the prefix LM, you know that you have some input that you don't want to generate, like some context, and so you are basically just taking the transformer decoder and modifying the mask to allow that portion to be fully unmasked. But the rest of it is the same. Really, it's like if you want to do conditional text generation, you probably want to use the prefix LM formulation. If you're just interested in generating text conditioned on other text, then like a normal prefix, then you can use the transformer decoder. Usually what happens is something like GPT-2 is trained in this fashion with like a transformer decoder. And then for someone who wants to use this model to solve their own text generation task, they take GPT-2 and they fine-tune it as a prefix LM. We'll talk about what that means later on in this class, hopefully. Okay, I'll hold all the questions till the end. Well, actually, I don't know. I'm running out of time, so maybe I'll just take more questions. Do you have a question?
Yes, I mean, unmasked means treating, right? So what's the benefit of like we get the perfect unmasked?
So the question is, if unmasked means cheating, what is a benefit here?
Yeah.
The point is that if you look up here, we are not generating, we're only generating tokens for the part of the sequence that we care about, which is, in this case, the English sequence, right? We aren't doing any generation for the input sequence, which is the French sentence. So there's no point in masking the attention on the French sentence because we don't care if we're cheating on the French side. We actually want to see all of the French tokens to have the best possible representations of that sentence. So if you're generating tokens, you need to be careful about cheating. If you're not generating tokens, so like in this case here, we're not generating tokens for the first 3 words, we should use unmasked attention.
I mean, what's the difference between if we just mask all everything?
Oh, so if you just masked everything?
Yeah.
I mean, you could do that, but then like F2 only knows about F1 and doesn't know about F3, right? So that's strictly worse than if F2 knew about all the other French words in the sentence, because again, our goal is not to generate F3, our goal is to generate the English words.
Okay, so it's not going to make more sense.
Yeah, I mean, this is basically just doing both the encoder and decoder jobs in one single model. Okay, let me check the YouTube. Will we talk about why transformers use GELU as its activation function? No, we won't talk about that. That's probably just a hyperparameter choice. So yeah, don't worry about it. I think neural architecture search has probably found many other variants. All right, so I think what I'll do is I will start explaining the transfer learning stuff and then let that go into next class where we'll focus on BERT. So let's get started. So we're going to switch topics for a bit now. We've covered like transformers, all their possible variants that you might see. And now we'll get to the actual main use case of these transformer language models. So note that at this point, we haven't actually talked about how you can use a model like this to solve any sort of NLP task. We've just sort of been focusing on language modeling. But now we'll talk about something else. So using neural LMs for transfer learning. So to introduce this, let's go back a couple years, maybe now more than a couple years, like pre-2017, 2018, when transformers hadn't been around and people weren't actually training these huge scale language models. How were they solving NLP tasks? So let's consider sentiment analysis. Again, in this task, you're given some text and you're asked to predict whether it's positive or negative about some like product review or movie review or something like that. So around 2013, this task was just starting to be tackled by neural network models. And one approach is just to, so if I have the sentence, this, that's an S, this movie is great, and I want to predict its sentiment, an easy thing to do is train an RNN on this on a labeled data set of movie reviews. So I get my hidden states. And at the final hidden state, so note that this is the hidden state over here that has all the information about this, this sentence. I'm going to put a softmax layer, predict positive. And so the key idea here is that this RNN, all of its parameters, all params of RNN are trained from scratch on labeled sentiment data. So there's no language model even anywhere near this, right? I have some labeled reviews. I put them all through a recurrent neural network. I tell the model to predict the ground truth label. I do backprop down into, you know, all of the hidden states, into the word embeddings, into those recurrent and embedding matrices that are part of this model's parameters. And at the end of the day, I get a model and I can use it for sentiment analysis. One of the issues with this, well, okay, so what are some issues of this approach? Someone said training time. If training time of this is an issue, then training time of the approaches that we're going to talk about is an enormous issue. That's not so the big issue here is that we are forcing the RNN to learn composition and world knowledge and many other linguistic properties just from a tiny labeled data set. So like imagine you were a baby and you had no knowledge of language at all, and the very first thing that you see is someone just downloads Amazon reviews and gives it to you and trains you to predict positive or negative. Like, you're not going to understand anything in these reviews, right? You might be able to draw some patterns like, oh, great and awesome are usually correlated with positive and terrible is negative, but you might not understand, you know, like the reputation of a brand, or you might not be able to put words together to form compositions. So if you say something is, so bad, that doesn't mean it's bad, right? That means it's like not so bad. So it's really not great to make a model learn everything it has to know about language from just a tiny labeled data set. So the intuition behind using language models for transfer learning is essentially, what if we repurpose a large-scale neural LM to solve this task? So if we are able to do this, now our model is not learning all this information just from sentiment data, right? Just from movie reviews. If you have a language model, you have data for free, right? As we've discussed, so you can train it on arbitrarily large data sets in many different domains and styles and so on. The model can learn a lot, as we saw, from just this simple objective of predicting the next word. This is actually a much better objective for learning composition or world knowledge than predicting whether a review is positive or negative. So if we have a language model that we've trained to predict the next word, it has a lot of information about compositionality and world knowledge and so on. Can we actually use this model to do sentiment analysis? And if so, how do we do it? So the very first, or among the first approaches in this regard, I was actually involved with. It was called ELMo, and it began this series of Muppet named models, which refers to embeddings from language models. So if we take this approach from 2013, we're just going to reuse it here. The idea behind ELMo was that, well, why do we have to train all of these parameters from scratch? Can we actually use some language model representations and integrate them into this model so that the recurrent neural network only has to learn how to extract the sentiment representation from these language model representations and does not have to learn composition or anything like that. So the key trick here is that these word embeddings come from a language model. So specifically, and I'll simplify some things here that you can read the ELMo paper for more details, but basically, if I have a language model, so let's say I have a recurrent language model, so C1, C2, C3, so let's say I have an RNN LM. So we've already seen how this works, right? It's similar to what we drew above, but instead of having the softmax layer at the end, here at every hidden state, I'm going to predict the next word. So language models can be trained on huge data sets because labels come for free. So in ELMo, we trained one of these language models on 1 billion words, which at that time was pretty big. And then we thought, these representations here, the hidden states of this RNN, they actually contain a lot of useful linguistic information about the input sentence. Far more than word embeddings that are learned from scratch from using, like a sentiment data set and an RNN trained on that. So if we take these representations here, the final layer hidden states, can we improve a sentiment model? And so essentially what we did was we replaced the word embeddings of the original sentiment network with the hidden states from the language model. So if I go back to this note, wow, that's not what I wanted to do. These come from the hidden states of the language model. And they are kept frozen during training. So in this case, the input to my sentiment recurrent neural network is frozen representations from an RNN language model. And the sentiment network now, let me delete this. The sentiment network only needs to learn how to get the information about the positive or negative sentiment out of these powerful representations of the sentence. Note that these are not learned from scratch anymore. And so this is an instance of transfer learning. You have a big, powerful language model that you're using to get representations of a piece of text. And then you have some smaller model on top that is used to get some information of interest out of these representations. So now the sentiment RNN doesn't have to do all the work from scratch, right? Instead, the language model is the one relied on to do composition and extract the relevant world knowledge and so on. And this RNN up here is only used to get some sentiment out of these vectors. So we'll talk more about this in the next class, and also we'll talk about BERT, which is a scaled up transformer variant that uses the same idea. Do you have a question?
So when you say frozen, do you mean C1, C2, C3 will never not be a parameter of this one?
Yes, that's a great question for clarification. So when I say these are frozen and they're kept frozen during training, I mean that there is no C1, C2, C3, C4 as part of the model parameters anymore. Those are replaced with something that's learned from a language model. So they are not parameters in this higher level sentiment model. Yeah?
Why are you taking the hidden layers of RNN?
The question is, why are we taking the hidden layer of the RNN? So these hidden layers are specialized to predicting the next word, right? And so if you remember, we looked at some examples where this task of predicting the next word requires a lot of semantic and syntactic knowledge about the prefix, right? So you might need to know, what syntactic structure is of the phrase that you're currently in, or that the word eat is usually followed by some food, some world knowledge like that. So there's a lot of information that is useful for sentiment and for a lot of other tasks packed into those vectors. And we're not going to be able to replicate that by learning these word embeddings from scratch. That's the idea. Okay, are decoder models good for text classification? They can be good. We will talk about that when we talk about T5, but they're not particularly specialized for text classification because you actually have to generate the label if you're going to use a decoder for this. So yeah, basically you want to use encoder models more often than not when you're talking about text classification. And in the next class, we'll talk about BERT, which is one instance of an encoder-only transformer model that's useful for a bunch of different NLP tasks. So before we end, note that next week is a holiday, so we have class on Tuesday and Wednesday, which is pretty annoying. And your project proposal deadline was extended to not this Friday, but the next Friday. So hopefully you can use that more time, the more time to write a better proposal.